In this video, I want to take a look at the definition of orthogonal. Let's jump right in here. Two vectors, u and v, in Rn are said to be orthogonal if their dot product is equal to 0. Now, remember, the dot product is, at least the geometric interpretation, the length of one times the length of the other times the cosine of the angle. So if the dot product is equal to 0, then that angle is essentially pi over 2, right? When is the cosine equal to 0? Well, at 90 degrees, or pi over 2. I'm not going to use degrees anymore. It's interesting to me that the textbook we use also has, in the definition, it has the line, we will also agree that the zero vector is orthogonal to every vector in Rn. And I look at that and I say, well, the zero vector certainly satisfies the definition you've already given. Because if you take the zero vector and dot it with any other vector, it's going to be 0. Each component of that other vector is going to be multiplied by a 0, and then all those zeros add up, so you're going to get 0. So yes, the zero vector is orthogonal to any other vector because it satisfies the definition. We don't have to make a special compensation here, or dispensation, whatever the right word is, to say that, oh yeah, we also throw the zero vector in. Now, I see why the book might be saying this, but I don't think they needed to. The notion of orthogonal is essentially the notion of perpendicular, right? In R2 and R3, we know what it means for two vectors to be, or two lines, or two line segments, whatever, to be perpendicular. The angle between them is pi over 2. But we didn't define orthogonal as the angle between the two vectors is pi over 2. Because if we did that, then we would have to make that special compensation for 0, because you can't find the angle between a 0 vector and something else. Because remember, here's the definition of the geometric definition of the dot product, right? So to find the angle, I'd have to divide by both lengths and then take the inverse cosine. Well, if one of those vectors was a 0 vector, I can't divide by the lengths. Okay. Now, also thinking of it from the point of view of orthogonality, if you get a dot product equal to 0, it means that one of the three factors over here had to be equal to 0. So either one of the two vectors was a 0 vector, or the angle between the two vectors was pi over 2, right? And so I see that's, I think, why they're making that special comment about the 0 vector, is because they're thinking, oh, well, the dot product got to be 0 for a different reason than all the other times, right? If u and v are not 0 vectors, then the only way the dot product is going to be 0 is if the angle is pi over 2. But that's not what their definition was. They're orthogonal if the dot product is 0. So yes, 0 is orthogonal to everything. Okay. When we use the word orthogonal, you can think a synonym perpendicular, that the two vectors are at right angles to each other. Okay. Here's an example. In R2, here's the vector 1, 2 and the vector minus 4, 2. If I take the dot product, I'd have 1 times negative 4 plus 2 times 2, which would be negative 4 plus 4 is 0. Now, in R2, I can actually just plot the points and you can see, or plot the vectors, and you can see that indeed they look perpendicular, that's a 90-degree angle there. Sorry, not going to use degrees anymore. It's pi over 2, and they're orthogonal to each other. Here's another example in R4. Vector 1, 2, 3, 4 and the vector 1, 2, 3, negative 3.5. When I take the dot product, I get 1 times 1, I get 2 times 2, I get 3 times 3, I get 4 times negative 3.5 for a total of 1 plus 4 plus 9 minus 14, and the net result is 0. Now, it's hard for me to plot those points in R4. I have ways of visualizing it, but I know what they look like. They look kind of like this. Now, I've specifically made one of them a little longer than the other, because the fourth component of this one 4 is a little bit bigger than that one, but they're perpendicular to each other. Their dot product is 0. They're orthogonal. They're not 0 vectors, so the angle between them must be pi over 2. So I know what they look like. They look like this. It's just that they're tipped out into the fourth dimension somewhere. But if I could tip my head that way and look at them, I would see two vectors at a right angle to each other. Okay. Orthogonality. Two vectors are orthogonal if their dot product is equal to 0.